Okay, today we are going to finish electrochemistry and then make a decent amount of headway into our next major unit of this course. But first, just to remind ourselves, last time we finally got into how electrochemistry is used analytically in the form of this device called an ion-sensitive electrode, or ISE for short. And the type of ISE that we are focusing on in this class is the pH probe, which is one of the more common ISEs. Some of you have probably used one in a lab before, and it ties in nicely to our prior unit of acids and bases. And so let's quickly recap what we covered and then go further with it. So to recap what we learned about the pH meter or pH probe is that it's actually a device that consists of two electrodes, each of which is exposed to a solution containing protons. And ideally, this probe is designed in a way so that each electron only senses protons in solution, and voltages that are generated are based solely on that species and nothing else. Now, if the proton concentrations in both solutions were equal, then there would be no voltage. But if there is a difference in concentration, therefore a difference in pH between the two solutions, a potential exists. And we went into the logic of why that is in the last lecture. We recognize that the voltage difference as measured by a voltmeter is just going to be the difference between the voltage on one electrode minus the other. We then re-express these voltages in terms of the Nernst equation, where the only species that we entered into the Q portion of the equations were those protons, because again, ideally only protons are sensed by the electrodes and generate a voltage. From there, numerous algebraic steps can be done to re-express that equation in a much more compact manner, in which ultimately the voltage measured by this pH probe system can be related to the difference in pH values between the analyte that we are studying and some reference solution that we know the pH value of. And this reference solution is in contact with the electrode that is ultimately hooked up to the positive terminal, while the analyte is in contact with the electrode that is hooked up to the negative terminal. Now this whole equation you should have in your notes, but let's add one more little piece to it, and then we'll make sense of it with a visual. Under the analyte, write the word outer, and under the reference, write the word inner. And to understand what I mean by outer and inner, we need only look at an image of a pH probe. So here's the pH probe picture that's given in the book, and this is me trying to redraw it in PowerPoint with some color coding to make it a little bit more digestible. So a pH meter is what's known as a combination electrode, where both electrodes are contained in the same unit, and they are divided into two separate compartments, the outer compartment and the inner compartment. And that's what those outer and inner labels are for. So let's break this down section by section, starting with the inner electrode. So attached to the positive terminal of some type of voltmeter, we have a silver solid wire, and then coating that wire is some silver chloride paste. So that's our reference electrode, silver chloride. We've seen this before. This silver chloride electrode is in contact with a solution that contains some fixed concentration of HCl and thus some fixed concentration of protons. So that's our reference solution where we know everything about it. It's in the inner tube hooked up to the positive terminal, which agrees with what you have in your notes for the pH probe equation. Now, in the outer tube, we have a similar situation. We have a silver wire hooked up to the negative terminal. Towards the end, the silver wire is coated in silver chloride paste, so we have another silver chloride electrode. This is in contact with some aqueous solution that's saturated in KCl. There's also some AgCl dissolved in solution coming off of this paste here, but we're not going to be concerned with that. What matters to us isn't so much what's contained in this solution here, so much as what it's ultimately in contact with. So we can see from this picture that this pH probe is put in some analyte solution, presumably with some proton concentration that we are interested in knowing. And some of those protons in solution will adsorb to the outside of this glass bulb. The protons will then be sensed in a manner through the glass by this outer electrode here, while this inner electrode is sensing these protons that it's in contact with. If these concentrations are different, Once again, a voltage will be generated and be measured by some voltmeter. Now, admittedly, the actual mechanics of how these H+ ions on the outside are sensed by this electrode through that glass is rather complicated and well beyond the scope of this course. Here's a 2-page excerpt from an electrochemistry book that actually goes into the ins and outs of this whole system. And this goes on for quite a few pages, so we are absolutely not going to cover that in this course. I would rather watch Cats. Maybe. So that's all we're going to cover regarding the design. But I do want to update that pH meter equation a little bit to incorporate two other terms. One is a constant that just has to do with non-proton factors contributing to the voltage. Because again, the idea that only protons will be sensed by these electrodes and generate a voltage is an idealism. The other term is this beta symbol, which stands for asymmetry potential. It accounts for the fact that no two sides of a material are truly identical. In the context of a pH probe, what it's addressing is the fact that the glass on the inside of this bulb is not identical to the glass that's on the outside of the bulb, and that will have some minor effect on the generated voltage. But notice, at most, it causes this value here to deviate to 0.98 of its normal value. And in this class, we will always assume it's just going to be equal to 1.00, so we won't take it into account in our problems. But if you're following along in the book and you see this beta symbol, I want you to know what that is. And so if you haven't written this down yet, pause the video really quick and get it in your notes. To actually see this equation in action, we'll do a clicker. And because it's important for the next video, I will actually do this clicker in the video. But you should still pause it and give yourself like 2 or 3 minutes to try this on your own. At first glance, this problem may seem impossible because it seems like I haven't given you some key pieces of information. But if you set everything up correctly, you'll see that you don't actually need those pieces, and this is completely doable. So here's how we do it. We're not actually given an objective voltage value in this problem. We're given a voltage change of 100. In other words, we're measuring the voltage at some time, which we'll just label as E2, and we'll say that's the second time we're measuring it, and we measured it originally, and the difference between those two is 100 millivolts. And so given that this problem's ultimately based on two different voltage measurements, I wind up having to write that pH probe equation twice. And so it winds up looking like this. This will be equal to, in brackets, constant, which was not given to us in this problem, but we don't need it, plus 0.05916 times, in parentheses, the pH of the analyte that we're interested in minus the pH of that inner reference, which is kept constant, which we're also not given in this problem, but we don't need it. Close parentheses, close brackets, and we'll say that this represents that voltage when we take it the second time after it's increased by 100 millivolts. And then I'm going to write the equation again. Constant plus 0.05916 parentheses pH of the analyte minus that inner reference constant pH. But this represents that first voltage reading. And the one thing that's missing from the right side of the equation is this minus sign here. So let's add that in. And when we have everything lined up like this and have that subtraction sign, you can hopefully see that some of these terms will cancel out. We don't know what the constant is, but we know that it's not going to change between the first and second reading, or that would be a terrible constant. And so a number minus itself is 0. We can do the same for the pH of that inner solution. We don't know what it is, but it's supposed to be kept constant based on the notes we discussed earlier. Thus, all of this actually simplifies to 0.05916 parentheses pH of the analyte upon the second reading minus pH of the analyte upon the first reading. And this in turn must equal that voltage difference, which is 100.0 millivolts, but we need to convert that into volts, so it's 0.1000 volts. And the reason I know it has to be in volts is because if we actually go into where this number came from, we would have units of volts left over. I've just been ignoring the units this whole time. From here, I'll leave it to you to figure out what to do with this pH value and to determine which answer is correct. We'll finish it in Zoom.